Hello and welcome back to the Calculus 1 playlist. So in today's video, we're going to be going over several examples of the sequences that we were covering in the last video. So in the last video, if you recall, we kind of defined what sequences are, talked about some of the properties of sequences and converging sequences, talked about what it means for a sequence to be bounded and monotonic, as well as the monotonic sequence theorem. So in this video now, we're going to be doing examples kind of explaining the process and steps of how to solve those types of problems. So without further ado, let's begin. So example 1. And so in example 1, we're going to show if the sequence a of n, which is equal to 5n squared minus 14n plus 6, all divided by 4n squared minus 6n plus 3 converges. And so if you recall, we want to see, to find if a sequence converges, we need to use its limit as it goes towards infinity. So we'll say the limit as n approaches infinity will be 5n squared minus 14n plus 6 all over 4n squared minus 6n plus 3. And if you guys would like, feel free to pause the video and solve these problems on your own, but I'll be going over the in-depth explanation of how to solve this problem. But yes, how do we solve a problem like this? So in the last video, we introduced this limit notation, and in the next video, we'll talk more about it and give it a formal definition. But how do we solve a limit in this sort of format? Well, we need to do some algebraic manipulation to get it into the form that we'd like it to be in. So what I'm going to do is pull an n squared out of the numerator and the denominator. And it might seem arbitrary at first, but you'll see why later on. So pulling an n squared out of the numerator, we get 5 minus 14 over n plus 6 over n squared. And over the denominator, we'll have, this becomes n squared, and we'll have 4 minus 6 over n plus 3 over n squared. And right away, you can see that these n squareds will cancel. Great, that makes our life easier. So again, we'll have our limit as n approaches infinity, and we'll write it in this new form, 5 minus 14 over n plus 6 over n squared all over 4 minus 6 over n plus 3 over n squared. Great. So why do we actually write in this form? Well, it turns out the limit as n approaches infinity, oh, that's 8, sorry, as n approaches infinity of 1 over n equals to 0. Well, why is that the case? Well, recall, if we're saying n approaches infinity, we're saying as n gets infinitesimally be bigger, or just it gets as huge as possible, how does 1 over n behave? Well, 1 over n, you can see, so if you had 1 over 10 is equal to 0.1, but if you had 1 over 100, it gets 0.01, and 1 over 1,000 becomes 0.001. So it just gets smaller and smaller and smaller, and it approaches 0. So the limit as n approaches infinity of 1 over n is going to equal to 0. And that's the same for any kind of number over n. So for these cases, as you see, we have 14 over n, or 6 over n squared, or 6 over n, and 3 over n squared here in our our limit value. Well, if we plugged in infinity on the denominator of those kind of parts of our equation, then they would just approach 0. So let's actually do that. Let's say we equal, then we'll evaluate this limit. So we have 5 minus 14 over infinity, well, that's 0, plus 6 over infinity squared, that's 0. And recall, infinity is not an actual number. It's just a construct. It just means as we get larger and larger and larger, what happens to our function value. So minus 6 over infinity, well, again, 0, and 3 over infinity squared, again, 0. So then our limit is just 5 over 4. And I dropped the limit notation once I evaluated what n equals to infinity is like. So that's something, again, we'll cover much more detail in the next video. We just need to learn how to use limits in this video. But again, so we see that our value is 5 over 4, and if it approaches some value, if our limit is equal to some value, then our sequence converges to this value. So sequence converges to 5 over 4. That's the value. Great. Next example. does our sequence a of n equal to 1 over 5n plus 2 converge? Great, same thing. So we'll have the limit as n approaches infinity of 1 over 5n plus 2. I'll write this m better. So what do we do here in this case? Well, again, we can just look at this straight away and said, okay, if we evaluated this, if we said 1 over 5 to infinity plus 2, well, our denominator would just get infinitesimally big. It would just keep growing, growing, growing exponentially. And our numerator is just 1. So our value will approach 0. So we can just say straight away, our sequence converges to 0. So the sequence converges. Great. So next example. So that was example 2. This is example 3. Does b of n equals to cos of n converge? Great, so we'll write it in limit notation as well. Limit as n approaches infinity of, and we'll have our equation, our sequence value, cos of n. So does it converge? How would we approach this? Well, we also need to understand the properties of our sequence when we're evaluating these limits. If you look at the graph of cos of n, you know that it's an oscillatory function. So let's draw out some of the terms of cos of n. We'll draw out the continuous f of x is equal to cos of x. Well, this is kind of what that looks like. So you could say that this what's called sequence is oscillating between -1 and 1. It's bounded by -1 and 1, but never tends towards any of them. It will go on in this form forever. It will be this wave form forever. So the values of the sequence would just kind of go like this forever. They wouldn't tend to a specific value. So we would say that this is divergent. It does not converge. Cos of n does not converge because it is oscillating between -1 and 1. Great. So let's do a harder example now. We've done a few easier examples, but let's step up the complexity a bit. Does a of n, our sequence a of n, which is equal to n cos of 2n all over 2n squared plus 3 converge? Great. So let's write it in limit form again. Limit as n approaches infinity, and we'll have n cos of 2n all over 2n squared plus 3. Well, you might be tempted again to say that it oscillates because of this cos 2n term, but that's actually not the case. And to solve this problem, we'll need to use the squeeze theorem. So use the squeeze theorem. So if you recall, we said that the cos sequence oscillates between -1 and 1. Well, we can also just say the same about cos of 2n, right? If we just apply a 2n transformation to the n, all it does is it changes the frequency of the waveform. It doesn't change the amplitude, so it stays between -1 and 1, right? But we need to use the squeeze theorem somehow to solve this problem. And if you recall, the squeeze theorem itself is defined like this. So we say we have 3 sequences. Sequences are an, bn, and cn. Well, if an, bn, cn are such, so bn is bounded by an and cn, and we say that the limit as n approaches infinity of an is equal to L, and the limit of n approaches infinity of cn is equal to L, then since the middle equation is, or middle sequence is bounded by these two sequences, we can say that this limit, limit as n approaches infinity of Bn is equal to L. And we need to prove that somehow. So I'm going to construct our limit inequality as such, and I'll show you what I mean. So we'll have -1 is less than or equal to cos of 2n less than or equal to 1. Let's multiply every side by n, sorry. So I have -n, oops, sorry about that. I have n right here, cos of 2n, and n here. And then we'll divide everything. So we'll have this, divide everything by 2n squared plus 3. So we have 2n squared plus 3, and cos of 2n, and oops, 2n squared here, 2n squared plus 3, and you have n, 2n squared plus 3. Great. Now this in the middle is our original limit, right? This is our original sequence that we're trying to solve for. So if we prove that this limit or this sequence, these two sequences, the bounding sequences approach a specific value that is the same, then we can say that this middle sequence, the sequence that's being bounded by the two sequences, is also approaching the same value. So in this case, our AN is this, and our CN is this, and BN is this guy. So let's evaluate the limits at the endpoints. So the limit as n approaches infinity of -n over 2n squared plus 3, well, we can go ahead and do limit of n, so we'll pull out an n, the highest term from the top, and n squared here, and we'll have 2 plus 3 over n as n approaches infinity. Well, this will cancel like that. So then we'll have the limit of 1 over n, 2 plus 3 of n for n approaches infinity. Well, it turns out that this will just equal to 0. And the reason being is because we have this n term on the bottom that will just grow exponentially, making our denominator grow exponentially forever. And since our denominator is exponentially growing and our numerator is 1, then we'll have a limit value of 0. So for the other bound, we'll have n 2n squared plus 3. Well, the limit of n approaches infinity, if we did the exact same thing, I noticed I dropped the negative sign, that's my apologies, would have like this, and the same result we'd have as n approaches infinity would be 1 over n, 2 plus 3 over n, and that's equal to 0. So you'll get the same result, except one of them has a negative sign, the other does not, but 0 is still equal to 0. It doesn't matter. We'll arrive at the same result. And since the two bounding sequences are arriving at the same limit as n approaches infinity, then we can say then, therefore, by squeeze theorem, that the limit of n approaches infinity of, not 2, of n cos of 2n all over 2n squared plus 3 equals to 0, so it converges. Right, so all we did here, right, is take our cos term that's inside of our sequence right here, and we kind of constructed our original sequence from that, including our bound points. So we had -1 to 1, and we transformed that and transformed it again until we had our original function or an original sequence bounded by two separate sequences. The two separate sequences approached a limit value of 0. Therefore, our middle sequence had to approach a value of 0. So a lot of steps, but overall not too difficult to understand. So the next example. So does a of n, sequence a of n, equal to -1 over n converge? So let's write down the limit for this. Limit of n approaches infinity of -1 of n, right? So if we plugged in infinity, we wouldn't really have anything that's happening, right? We don't know what's happening. So let's actually just evaluate the first few terms of this sequence. So when n is when n is equal to 1, we just have -1. When n is equal to 2, we'd have 1. When n is equal to 3, we'd have -1. When n is equal to 4, we'd have 1. When n is equal to 5, we'd have -1. And you could see this pattern will just go on forever, right? So if we looked at it graphically speaking, this is what our sequence kind of looks like. We'll have this term here, 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 here. It goes back and forth, and it would behave like this forever. So we can say that -1 to n diverges. It doesn't converge to a specific sequence. It always will be oscillating back and forth between the values 1 and -1. So that was easy. Well, let's do another example. And we'll do, does an equal to -1 to n, and we'd have 3n squared plus 4n all over 4n cubed plus 5n converge, right? And again, you might be looking at, okay, we have this -1 over n term, what can we do? Well, there's another property of limits that we haven't talked about, and it's known as absolute convergence. So I can say that theorem, the limit of n approaches to infinity of the absolute value of a sequence is equal to 0, and this is known as absolute convergence. Right, so if we kind of apply this process to this question, we can derive a solution, a converging solution. So let's do this. So the limit as n approaches infinity of -1 to n, 3n squared plus 4n all over 4n cubed plus 5n, and we'd have it like this. Oh, sorry, not absolute value. We'll have the absolute values here on the outside. Well, what happens to -1 over n, this term? Let's look at this term by itself. Well, as you recall, right here, we said the values oscillate back and forth between -1 and 1, right? So they don't change. So the absolute value of this term is always going to be equivalent to 1. So it doesn't change. It's not a variable of anything. It doesn't change regardless of your n value. So we can actually remove this from the limit. We can just say that it's equal to 1. So limit of of n approaches to infinity of 1 times, and we'll have 3n squared plus 4n all over 4n cubed plus 5n. We have this absolute value sign. Well, it turns out that this, if we factor out the n squareds, we'll have n squared on the top, and we'll have 3 plus 4 over n, and on the bottom we'd have n cubed plus 4 plus 5 over n squared. Well, it turns out that that's just equal to 0, because the n squared, this cancels, and this becomes n. And so recall, we could say that this term will go to 0, that term will go to 0, but since we have this n term on the bottom, our value will just always approach infinity. Therefore, since our denominator dominates, I guess, the expression, it's increasing very rapidly compared to the numerator, we would say we have the limit equal to 0 and absolute convergence. So that's a neat trick to do in sequences. So let's do another example, and this will be using induction, mathematical induction. So let's say we have a sequence it's represented as an, where n is equal to 1 and goes to infinity, of positive numbers is defined recursively by and we'll have these values. A1 is equal to 1, and an plus 1 is equal to 3 minus 1 over an, right? And so recall recursively, if you've never heard this word before, it just means that the next value of a specific sequence depends on the previous value. So an example would be like a Fibonacci sequence. Where the way to get the next value of your sequence is you need to have some sort of relation to the previous values. So in this case, you can see that the next term, n plus 1, is 3 minus 1 divided by the previous term. So we want to prove that an is less than an plus 1 for all n is an element of the natural number system. So i.e., we want to show monotonic increasing. So we just want to show that this sequence is increasing forever because the next term, an plus 1, will be bigger than an. So, and we're going to do this by induction. So recall, if we're doing induction, we have our base case. Well, we need to prove that the first term is less than the second term. Well, a1 is equal to 1, and an plus 1, which is 2, a2 is equal to 3 minus 1 over 1, which is equal to 2. So 3 minus 1 is equal to 2. We see that 2 is bigger than 1. Therefore, we can say that A1 is less than A2, which is good. Now we need to do the induction hypothesis. Assume that AK is less than AK plus 1, right? So we need to find a way to show that AK, or we're going to assume for the induction hypothesis, and I'll write I dot H here, that AK plus 1 is bigger than AK, and this is true for all n is equal to k, and n is an element of the natural number system. Great, so for the induction step, so number 3, we need to prove AK plus 1 is less than AK plus 2. So that's what we need to arrive to. That's what we need to get to. But how do we actually get to this value? How do we prove this? Well, let's go ahead and start by using our induction hypothesis. Recall, we're going to have to use our induction hypothesis in some way. So again, I'm going to construct my previous sequence. So this sequence right here using my inequality on both sides. So we're going to first take 1 over, or the reciprocal of our inequalities. So we'll have 1 over AK is less than 1 over AK plus 1. And then we're going to multiply this by a negative sign. So negative AK and negative 1 over AK plus 1. And then we're going to add 3 to both sides. So 3 minus 1 over AK is less than it's going to be 3 right here. 3 minus 1 over AK plus 1. Well, let's think about this. We said that an plus 1 is equal to 3 minus 1 over a over n, right? So in that same way, we can say that AK plus 1 is equivalent to this, and therefore AK plus 2 is equivalent to this. So we've arrived at our induction step just by recreating the conditions of our previous sequence. So we just set everything to be similar to this form, and we could say that that's equivalent to the next value of our sequence. So proved, marker is not doing well, proved monotonically increasing by induction. Great. Let's look at our last example, and it'll be similar to this. I've seen this one in another video, and I thought this is a very, very good example. So consider, we'll have this sequence, C of n is equal to, or this is the sequence, as n is equal to 1 and goes to infinity, is defined recursively, by C1 is equal to 1, Cn plus 1 is equal to 6 plus Cn raised to 1/2. So for part A, show that it is monotonically increasing. Right. So we'll have this kind of sequence, and we need to prove monotonic increasing, just as we did in the previous video, in the previous example. So all that it is we're going to reconstruct our induction process. So we're going to have induction base case. Oops. Lower induction base case. So again, C1 is equal to 1, and C2 in this case is going to equal to 6 plus 1, all raised to 1/2. Well, that's just equal to root 7. And we can say then that 1 is less than root 7. Therefore, C1 is less than C2, which is good. Then we need to do our induction, our induction hypothesis. So assume, and we're going to just assume that we have CK being less than CK plus 1, right? And lastly, the induction step, we need to prove that CK plus 1 is going to be less than CK plus 2. So exact similar to the previous kind of example. We have we'll start with our induction hypothesis, right? And then now in this case, we're going to want to add a 6 here and then apply a 1/2 power or square root to both sides. So we'll have CK, my marker is not working, sorry. CK plus 6, 1/2. CK plus 1 plus 6, 1/2. So all we did is we just added 6 and applied a 1/2 to both sides. Well, this is just equal to CK plus 1, and this is equal to CK plus 2. So we proved that it's monotonically increasing. So that part is done. And I'm moving a bit quicker because, again, we've done this, we did this exactly in the last example. But the one I wanted to show you is here. Show that the sequence is bounded between 1 and 3. So Cn being less than or equal to 1, or greater than or equal to 1, but less than or equal to 3. Perfect. So again, we're going to do construction. We're going to do by construction, and but to do this again, we're going to use induction. So first, base case. So we have C of 1 is equal to 1. Well, 1 is less than or equal to 1, which is less than or equal to 3. Perfect. Next step. Induction hypothesis. Assume, and we're going to assume that 1, CK, and 3. Perfect. And last but not least, we're going to do the induction step. We're going to show that 1 is less than or equal to CK plus 1, which is less than or equal to 3. Well, how do we do this? We're going to use the induction hypothesis. So we're going to go by construction again. So we're going to add 6. So 1 plus 6, CK plus 6, 3 plus 6. And so that is equal to 7, CK plus 6, and 9. and we're going to apply a square root or a 1/2 to all the terms. So this becomes root 7. This becomes, again, if you see, we have ck plus 6 raised to the 1/2. Well, that's just equivalent to ck plus 1, cn plus 1, or ck plus 1. So I have ck plus 1, and this is 3. But hold on, this is exactly what we want, because root 7 is greater than or equal to 1. So we can say then that 1 root 7 ck plus 1 and 3. Thus, we can equivalently write ck plus 1, 1, and 3. But this is exactly what we wanted to prove in our induction hypothesis through our induction step. So there you have it. Those are a lot of problems using the sequences and I guess using limits to solve sequences and find convergence of different values. If you needed any help or any problems, please feel free to leave any comments. And yeah, in our next video, we'll start our discussion with limits. So take care, and I'll see you guys.